time I defined IZ fibrations for ordinary of one categories. So, and explain briefly why this is important notion from the point of view of model category theory. So I want to start today's lecture with a definition of an isofibration between infinity categories. So a functor, let's call this P from C to D of infinity categories is an isofibration so if it has the following two conditions. So first, P is an inner fibration. Oh, this is always true just by definition. And the second property is the variation of that property that I defined for just ordinary categories. So more precisely, I'm just repeating the condition. So for any vertex little c in the category C and any isomorphism G from the P of C to the D, so that's an isomorphism in the D. So there is another vertex C prime in the C, and there is an isomorphism F from C to the C prime such that if you apply P to this isomorphism, you'll get exactly G. So that's just a formal rewriting of the same that we saw last time. And you can also think, and this is for infinity categories, it's a little bit more useful in terms of the lifting problems. So you can take the zero vertex, which is included into the standard one-dimensional simplex delta 1. So here, well, since we're almost interested in the isomorphisms, I can consider the maximal subgroupoid of the C and D, look at the induced functor of this maximal subgroupoids, right? So then consider the corresponding commutative square, and the corresponding commutative square is exactly the data that we have, right? So this 0 corresponds to this vertex C, this G is represented by this map from the delta 1 to the maximal subgroupoid of D. And the existence of the lift is precisely the existence of this isomorphism F. So we can rewrite this as this lifting problem, but well, you can notice that unfortunately this is not for the C and D, this is for the maximal subgroupoids of C and D. Okay, so then there are trivial remarks and trivial propositions, so I'm not going to prove the next two propositions since they're very simple and we don't have that much time left in the course. So first remark is that, well, it's kind of not completely symmetric, right? So I can leave this vertex, I can kind of consider a condition like this, or I can do the other way around. I can, for example, take some D prime that is here, and so then there will be P of C prime here. So this is called condition 2. So say remark, condition 2 has a dual version. Let me call this condition 2 prime. And well, this is what I just said. So for any C in the C0 and for any isomorphism, now let's call this G prime from the D prime to the P of C. So to indicate this isomorphism, I just decorate this arrow. And yeah, so then conclusion is as before. There is C prime in the C and there is an isomorphism F prime from the C prime to the C such that P of F is equal to the G. P of what? P of F prime, G prime equal to the G prime. So if you just work with the categories, it's clear that condition 2 and condition 2 prime are equivalent, because you can, to go from one condition to another, you just use G inverse or G prime inverse. So these conditions are the same. And for infinity categories, they're still the same. but it requires a little work, and I'm going to leave this work as an exercise. So
shouldn't we write for all G prime instead of
yeah, for any isomorphism, yes, thank you. For any isomorphism G prime, there is this another vertex, and there is a lift of isomorphism. Yeah, so maybe let me just finish this remark. So for one categories, clearly 2 is equivalent to the 2 prime, and this has observation, well, and well, I don't know, maybe I finish with this, and then I just formulate the proposition. So the proposition says that actually everything you need to know about this condition for either fibration comes from the ordinary category theory. So an inner fibration P from C to D is an isofibration if and only if you look at the what this thing induces on the homotopy category. So if and only if H of P from the H of C to the H of D is an isofibration, but that's for the ordinary categories. So proof is left as an exercise. It's not just a complete tautology. Well, you just kind of need to recall the definition of homotopy category and see how this works. That's also not hard. It's just maybe 2 or 3 lines. Okay, so this is a simple observation, and from this, since we know this property for ordinary categories, we immediately get the following corollary, which is clear. We don't need to prove anything here. So let me maybe, with the same notations as before, say that P, and notation for isofibrations. Maybe I need to introduce it here. So in the definition, so notation for the isofibrations is iso. We have notations for all fibrations, so this is just another class of fibrations. So P is an isofibration if and only if P opposite, induced on the opposite simplicial sets or infinity categories, is an isofibration. So this is true for ordinary categories, and this previous proposition reduces everything to the ordinary categories, so this is clear. You don't need to do anything if you have the proposition. And another such simple proposition, which is, if you just think about this for several minutes, you realize that this is completely tautological given this lifting problem, is the observation that, for example, left or right fibrations, so left fibrations union with the right fibrations, they are all isofibrations. Okay, so I'm leaving the simple statements as exercises and want to focus on something more interesting. Namely, I want to formulate and prove the following theorem, which is one of the important theorems in this course. So you notice that kind of in the proof I'll need the notion of isofibrations and I need the notion of the conservative functor, but actually to develop the theory of conservative functors and isofibrations, I need this theorem. So from this theorem you can derive a lot of corollaries, a lot of properties of different functors. So Joyal's. So this will be Joyal's extension theorem. And this is the simple version of his theorem. There is also Joyal's lifting, which more or less prove based on the same ideas. So let me say that, so let's assume that C is an infinity category. Well, I fix an edge in this category, so F is a map from delta 1 to the C, so that's an edge in this category. So then the following 3 conditions are equivalent. So the first condition is that F, is an isomorphism, in this infinity category. And the second condition, well, for any map A, this is from the left horn, so delta lambda n0 to the C. Well, n is at least 2. And also the assumption is that if you, kind of look at the beginning of this horn on the first edge of this horn, then this is given by f. So A restricted to the one simplex delta 0, 1, so this is f. Okay. So any such left horn admits an extension to the delta n, which is mapped to the C. So extension to the whole standard simplex. And condition 3 is just a dual version of this for any map B from the right horn lambda n to the C. N is at least 2. Now f is the last edge in this horn, so f is equal to the B restricted to the one simplex delta n minus 1n. And again, this admits an extension to the whole simplex. Okay. So this is the proof, and of course, as you can imagine, the conditions 2 and 3 are related by going to the opposite infinity category. So it's actually enough to prove that 1 is equivalent to 2 and 1 is equivalent to 3 is more or less the same, up to inverting some arrows. So let's prove that 1 implies 2. This is the interesting part of the proof. In the other direction is much easier. Okay. So first of all, well, I have this lifting problem that I need to solve, right? Let me rewrite this lifting problem a little bit differently. So remember that so for this lifting problem, I want to go to the adjoint, and we have this adjunction for lifting problems for the joints and for the slices. And when I formulate this adjunction in the proof, I kind of give you two diagrams which are equivalent. So now I'm going to use notation from those diagrams. So I just want to say that let me assume that A, I'm presenting you a dictionary how to relate this particular situation with that general statement and the proof of that general statement. So let's take A to be just a delta 1, zero-dimensional simplex. So B will be one-dimensional simplex delta with vertices 0 and 1. So I is an inclusion of A into B. So kind of the only obvious map that we can write here. So that's the map I. So L in this case will be the simplex with vertices 2 up to n. Right. So the K is the boundary of that L, and the J again is just the obvious inclusion of the boundary into the simplex. So Y, there was also Y in that statement. This is just delta 0. Well, the X is the given infinity category, and the map H is the map from the C to the Y. So if you go back to the statement about the adjunction between problems for the joints and for the simplices, you'll find that notation with A, B, L, K, I, J, X, Y, and H there. Okay, so this is what you need to take as those objects in this situation for the lifting problem in 2. And then here is the lifting problem, right? So we have this horn, lambda n0, which is mapped with the map A to the infinity category C, and also included into the standard simplex, and I want to construct this lift. So a simple exercise in combinatorics show you that this particular lifting problem is not equivalent, it's precisely the same lifting problem as follows. You just take the join of A and L and augmented coproduct with the B join K over A join with K. So this is mapped to the C, and again from the point of view of the given problem, this is map A, but from the point of view of the adjunction, this is U bar and V bar. So this A is the same as that pair. So then here the join of I and J, this is a map to the B join with L. So here there is also a point somewhere, there is a map H here, there is also a unique map here, and this is the lifting we're looking for, right? So for example, well, if you look at this join of the B and L, right? So B is a 1 simplex, L is an n-1 simplex. The join of two such simplexes is just the delta n. So this is a simplest situation that you need to observe here. And I left in the exercise, the assignment 3, similar exercise to verify that the join of such maps, kind of inside this simplex or inside this join, is precisely this map that is inclusion of the boundary. So this is based on that exercise essentially. So we can rewrite this given lifting problem as the lifting problem for the joins. So next I want to go to the adjoint problem for the slices. Okay. Oh yeah, so to finish this also in that statement about the adjunction of the two lifting problems, there was also map G, and that was true for any map G. So map G that I want to take in this situation, this will be by definition just the restriction of the map A to the L. So this is how I define that map G. So the equivalent lifting problem for the slices look as follows. So here I have still delta 0, which is included into the simplex with vertices 0, 1. So one simplex, map I. So here we consider the slice over G of C. This is the slice over composition of G and J. So this is map U. This is map V. And for shortness, I'm going to call this map here Q, but this is the same as the H to the box join with the index J, with index G and then J. Okay. Okay. So this is a joint lifting problem. So we're interested in this lift. And also, I want to add to this diagram a triangle. So there is a canonical map P, which is the map from the slice to the category. And if you take this composition of the P and F, you'll get back the map F, which you can immediately verify. Last time I computed how this map is acting on the simplexes. So this is an example of one simplex. If you do this, in this case, you'll get F. So we have a lifting problem, and we also have a commutative triangle. Okay. So then we need to do several observations. So first observation is that, for example, P is a right vibration, which follows from the general list of statements that I proved last time. So map from the slice of a category to the category is always a right vibration for this kind of slice over some map. So that's the right vibration. And here I need to know that any right vibration is a conservative functor. I proved last time that right and left vibrations are conservative. So here, hence, P is conservative. Right? But since this is conservative and this is some, so this is F is the edge that represents an isomorphism and P is conservative, we can make a conclusion that V is an isomorphism. So is an isomorphism, right? So this is one observation using that P is right vibration. Now, the second observation, again by the general properties from the last time, since I know that J in this situation is a monomorphism, as you can clearly see, that's an inclusion of the boundary of a simplex to the simplex. So this is in the cell with the bar. Those general properties imply that the map Q is a right vibration. Yes, that's a right vibration, right? And now I need to use that any right vibration is an isovibration. So Q is an isovibration. Right. So Q is an isovibration, and hence, right, so now this is a lifting problem, right? So this is a lifting problem exactly as in the definition of isovibration. So I have an object here, right, so this is just the point that represents an object in this category, and this is mapped to one of the vertices of this map here, and this is an isomorphism, so V is an isomorphism. Hence, there is this lift, and this lift is also an isomorphism. So there is a lift. Well, I don't want to give it a name, so this lift that we have in the lifting problem. And that's essentially the whole proof. As you can see, that's very short. Well, module some combinatorics that you'll do in the next assignment, and module our knowledge of the adjunction between two kinds of lifting problems. Okay, so then we need to go in the other direction. So let's assume that we have two, and we need to prove that one is correct. Well, this is kind of much more standard, and we've done such arguments many times, especially in the beginning of the course. So we can take, for example, we have solutions for all these lifting problems, right? So for example, we have this solution when n is equal to 2, right? So then we will consider the horn. So this n is equal to 2, and the missing phase is opposite to the 0. So I can consider horn like this. So this will be f on this phase and identity on the other phase. Okay, so then we know that kind of this is mapped, so this is map A, right? So from such horn to the C, right? So this is completely defines me a map with a given f. So and it has the extension to the whole simplex, which means that I can say that there is some other map, let me call this map alpha in the C1, such that the composition of the alpha and f is identity. So, and this is witnessed, so this composition is witnessed by the two simplex which we obtained by that extension, so from delta 2 to the C. Okay, so at least we immediately see that for this map F there is a left inverse, but then we consider again call this sigma 0 as we've done before. This is a map from the horn lambda 3 0 to the C, right? And I can give you a formal definition. So the formal definition is as follows. This lambda 0, if you restrict this to the phase delta 0, 1, 2, then this is tau that we defined before. So sigma 0 restricted to the delta 0, 1, 3, this is S1 of F. And the last one is sigma 0 restricted to the delta 0, 2, 3, and this is S0 of F. So that's a formal definition. So then for this phase we can take this map. So you can notice that restriction to the delta 0, 1 is precisely F. So there is an extension. So there is sigma, this is a map from the delta 3 to the C, right? And finally, we can take this sigma, restrict this to this additional new phase, this delta 1, 2, 3, and this is now a 2 simplex, and this is witness that alpha is a right inverse of f. Okay, so this is a formal stuff, but you can also draw a picture the same way as I've done in the beginning of the course. You have something like, well, this, and this. So let's just say this is 0, 1, 2, 3. So this is f alpha. So now with f alpha and id, this is the delta. Now this will be id f, and this will be also f. Okay, so I don't think that this is hard, since we've done such things so many times. Okay, so that's the proof of the Giles lifting problem. Now I don't want to prove the next theorem because it's based on more or less the same ideas. You just need to do some slight modifications. So I think it's quite natural, if you look at this statement, to replace this this lifting problem, right, to the kind of more general lifting problem where you have something here, some d here, instead of mapping to the point like here, and say that this map is just an inner vibration. And indeed you can do this. So this is, so I wanted to kind of do the proof in the simplest possible situation where everything is visible, and generalization I'm leaving as an exercise, but really it doesn't require any new ideas. So this is called Giles lifting. And the assumption now that, okay, let me call this pi. So this is from C to D. This is an inner vibration. So is an inner vibration of infinity categories. And I fix f, map from the delta 1 to the C. So this is an edge in the category C, such that the assumption is that the pi of f is an isomorphism. So of course this is an isomorphism in the infinity category D. Right, so before this condition kind of was missing because before D was just a point, so this is vacuous. So again, in this setting, the following three conditions are equivalent. So the first one, that f is an isomorphism in the category C, well, infinity category C. So the second one, well, I can kind of write again this in words, but I want to formulate this as a diagram for some lifting. So here I have horn lambda 0. There is some map A to the C. Here there is a pi, which is a map to the D, and the inclusion to the standard simplex, and another map that makes this square commutative. And to indicate this condition that I wrote here with the restriction, I can add here the inclusion of the simplex delta 0, 1. Right, so this is included here, and this composition is exactly map F. So to draw all the information on the same diagram. So the condition, of course, that every lifting problem, LP for shortness, has a solution. And that is for any n starting with 2. So this is condition number 2, and there is condition number 3, which is dual to the 2. So the idea of the proof is exactly the same. So you can essentially take this lifting problem, rewrite it again as in terms of the joins, go to the dual problem. Notice that in the dual problem you still get some maps like this, and this will be right vibrations by the general properties, and the rest of the proof is the same. So let me, for completeness, just formulate condition 3. Again, every lifting problem of this type has a solution for any n starting with 2, and here I take lambda and n, there is a map B to the category C, pi to the D, inclusion to the standard simplex. This is where we need the lift. And here there is delta n minus 1n, which is included in the horn, and this composition is a map F. Okay. So, well, I don't know. I can say that the proof is an exercise, but I think its modification is so clear that it's not really an exercise. Okay. So, for example, well, we can derive from this several statements, but for example, this one. So, an infinity category is an infinity groupoid if and only if it is a Kan complex. Now, this is a statement that I formulated before. I think I proved this in one direction, in the easy direction. Right? If you start with a Kan complex, you'll get an infinity groupoid. But the other direction is harder. And without this technique that we developed with the joins and slices and JL's lifting, I don't think that you can prove this. Well, at least I don't see how you can prove this. Well, you can kind of do this kind of arguments in particular cases, but it will be more or less the same proof. So, but with this technique, I think it's clear, right? Is it indeed clear? Well, we have an infinity category. Well, for example, if you go in one direction, we want to show that this is a Kan complex, right? But if this is a Kan complex, well, for the inner horns, we kind of already have the lifting, all the liftings, right? Because this is in infinity category. By definition, it has all the liftings for the inner horns. So what's left are left horns and right horns. But now, if you assume that you have an infinity groupoid, all the maps are isomorphisms, right? For example, you know that you have this isomorphism, right? So we still consider, well, that might be C to the point. This is an inner fibration, right? So if no, but this is really in both directions is the same. So if C is an infinity groupoid, right? So condition 1 here is satisfied, and we have all the such liftings. So then by JL's lifting, again, there are liftings for left and right horns. So here I'm using condition 2 and 3 together. Okay, and again, since this is a criterion, if I know that this is a Kan complex, well, I know that all such liftings exist, right? Because in the Kan complex I have not just inner liftings, but also left and right liftings, and then I'm going from the conditions, for example, 2, and derive that any map is an isomorphism. So really, it's kind of find it hard to explain the proof because it's so simple. Okay, but this is just another thing that we can do with the JL's lifting. So next, maybe I'll prove something about conservative functors, and then something about isofibrations. Okay. So proposition, and inner fibration P from C to the D. So this is C and D are infinity categories. Well, but we only defined, well, inner fibrations is defined for any simplicial sets. Well, but conservative functors only between infinity categories. It's okay. So between is conservative if and only if every lifting problem of the following type. So take the horn lambda n0, include this into the C, then there is P, which is mapped to the D. So the same diagram as before. So every lifting problem, so with the assumption, with additional assumption, when you consider the beginning edge of this horn, right, so this is called, say, phi. So with the additional assumption that the P of this phi is an isomorphism, in the category D. So for any n starting with 2, admits a solution. Okay, so this is a criterion for a functor to be conservative, given in terms of some lifting problems. So this is the lifting problem. Well, in one direction, if I go in this direction, so I assume P is conservative. Right, so let's assume that P is conservative. Well, I need to show that there is it's just a second. Yeah, so sure, this is a very simple observation. So if P is conservative, right, and we have an assumption that P of phi is an isomorphism, then we can say that the phi is an isomorphism. In C, right? But if this is an isomorphism in C, we have a solution of such lifting problem by the Giles lifting. So solution exists, a solution exists by the Giles lifting theorem. So in one direction, this is indeed simple. Okay. Now let's go in the other direction. So I'm assuming that I have a solution of any such lifting problem. So we have solutions for such lifting problems, and if I want to show that this functor P is conservative, I want to show that phi is an isomorphism. So I want to show the following, that phi is an isomorphism in the category C, right? If I can do this for any phi, then it means by definition that the functor is conservative. Okay. But now this is really the argument that we've seen before. This is the argument that I used when I proved that the left to right fibrations are conservative functors, right? Before I used the n is equal to 2. And that's really enough, right? So you consider case n equal to 2. You know that you have such a lifting. Well, and I also used this argument just here before I erased this, right? So you take the n equal to 2, the horn with the phi and identity. You construct the left inverse, right? And then you apply the same argument for this left inverse, and then you construct this left inverse again has a left inverse, so this left inverse is actually invertible, so this phi is invertible. So that's exactly the same as in the proof that left to right fibration is conservative. So in this case, left fibration. So and the proof is the same as in left fibrations are conservative. So I don't want to repeat the same argument. Okay. This is kind of a very simple statement with a simple proof, once we know the general J-L's lifting, but it has several important applications in the theory. So sometimes it's also called J-L's criterion for a functor to be conservative. Okay, so then we have the following corollary. Pullback of a conservative inner fibration is a conservative inner fibration. Okay, so the fact that inner fibrations are preserved by pullbacks we already know, since inner fibrations are core-saturated. So here, for example, we look at the pullback diagram. So let's assume that I have some D prime, which is mapped to the D. Here there is C prime, which is mapped to the D. There is a pullback. No, this is C. This is the pullback diagram. Well, maybe I can call this Q prime, this will be then Q, this will be P, and this will be P prime. Right, so that's a pullback diagram. So I'm assuming that P is an conservative inner fibration. I want to prove the same property for the P prime. And I want to use this proposition that I just proved. So I need to set up the lifting problem. So the lifting problem for this map P prime. So there will be a horn lambda n 0 mapped to the delta n, and the corresponding, well, maybe I don't draw anything at the moment. Yeah, and also, since this is important, additional condition in this lifting problem, delta 0, 1, first edge in this horn, and the composition is called phi. Okay, so maybe first sentence in the proof. We know that P prime is an inner fibration. Okay. Again, as I just explained, we know that the inner fibrations is defined as a core-saturated set. So this is an inner fibration. So the only question is about the being conservative, and let's use the proposition. So we assume that the P prime of the map phi is an isomorphism, right? So then Q, so Q, composition of Q and P prime of phi is an isomorphism, right? So since this is an isomorphism, so I'm just looking at the lifting problem for the original map pi, and I know that if this is an isomorphism, well, clearly this represents also, if I look at the map phi kind of phi prime that lives in this C and apply pi to this will be an isomorphism, right? Because if this is an isomorphism, this is an isomorphism, this is an isomorphism. So there is a solution. So there is a solution. Well, the solution like this. So maybe let me call this T. So there is a solution little t, right? And then of course there is a solution S, right? So then there is solution S, since C prime is a pullback. Well, just using the property of a pullback, I have this delta n, I have a map here, I have a map here, so there is a unique map S. Yes, S. Okay. And there is one more statement of this kind, but maybe since the proof is more based on more or less the same ideas on applying this proposition, and again it's quite simple, so I'm leaving this as an exercise. So another corollary. So given a pullback of infinity categories, so C maps to the D, so this is D prime and this is C prime, so that's a pullback diagram. And this map is P, and I assume that P is an inner fibration. Without this statement it won't be true, because I can't apply this proposition. So well, maybe I can even formulate it as follows, but this is kind of additional tautological part. So P is an inner fibration, say C, D, and D prime. These are infinity categories. So then the first very simple observation, C prime is an infinity category. And non-trivial statement is that we have the following pullback. I can take the pullback that is given and take everywhere maximal subgroup points. So when I go to the maximal subgroup points, I still get a pullback. So the proof is another exercise on applying Joyal's criterion, or you can apply this proposition, or you can. I think it's even easier if you directly apply Joyal's lifting theorem. So anyway, that's an exercise. Okay, so this is some simple properties of the conservative functors, which you can derive from the Joyal's lifting theorem. Now I want to prove something about another applications of the Joyal's theorem, but for isofibrations. Okay, so for either fibrations, I have the following proposition. Again, so let P from C to D be an inner fibration of infinity categories. So then the following conditions are equivalent. So the first condition, that the P is an isofibration. Condition 2, that functor induced to the maximal subgroup points is an isofibration. And condition 3 is that this functor on the maximal subgroup points is actually just a fibration, or confibration. So it has all the lifting properties for all the inclusions of the inner horns. So in particular, this is easy to see from this equivalence of these three conditions, but since this is important, I want to emphasize this. So in particular, an inner fibration between Kahn complexes is an isofibration if and only if, so that's an isofibration if and only if it is a fibration. Right? This follows from the equivalence of 2 and 3, right? If you assume that C and D are just Kahn complexes, this is infinity groupoids, so P is kick inside with the P with this symbol, P induced to the maximal subgroupoids. So isofibration is the same thing as fibration for Kahn complexes. So this in particular part is clear. So proof, well, we can independently, I think the easiest part is independently look at the 1 is equivalent to 2. And if you just think about this and just recall how I restated this definition of isofibration in terms of the lifting problems, you see this is immediately clear. There is nothing really to prove here. Right, because lifting problem for isofibrations already was defined in terms of the P induced to the maximal subgroupoids. So we only need to see that 2 is equivalent to 3. Okay. So this is again another application of Giles lifting. Well, so what is again? So I want to show that this is P induced to maximum subgroupoids is a fibration, right? But since I start with an inner fibration, so this thing is an inner fibration. We had this statement before, and this is also immediately follows more or less from the definition. So in this case, we know that this is inner fibration. So since this is an inner fibration, we have all these lifting properties for the inner horns, and to show that this is a fibration, so what's missing is just kind of two kinds of conditions. So first, you need to know that this is also true for the left and right horns, right? And you need to know that this is true for the case when n is equal to 1. Okay, so in this case, well, let me just maybe formulate it as follows. So let me, for shortness of the notation, set Q to be this P induced on the maximal groupoids, and think that in this case, C and D that I work with is just concomplexes. So Giles lifting give me the following. So if I consider the inclusion of the horn lambda n j into the delta n and consider the lifting problem for the Q, then this has a solution. So for any n which starts with 2 and for any index including the inner indices and j and n, right? So j is equal to 0 or n, this is Giles lifting, and for inner indices we already have this. Well, maybe Giles lifting plus the observation that Q is inner fibration. So together these two things give me that I have this lifting for n which is at least 2. And finally, we can notice that the Q is an isofibration. Well, again, we can formulate this in an equivalent way just from the definition of isofibration, is that I have the following lifting property: delta 1, 0, which is included into the delta 1, has a lifting property for the Q, and this is equivalent, well, really being isofibration is equivalent to both of these conditions, but I can formulate it like this. Yeah, so again, lifting for the Q. No, because this is precisely, this is just the inclusion of the 0 and 1, right? And that's the lifting problem. Well, this is just a definition of isofibration. So this thing is definition of isofibration in terms of what I called condition 2 or 2 prime, and they are satisfied since we have isofibration. And this is Giles lifting, since we work with the concomplexes in any map with an isomorphism. Okay. So that's a simple statement that will be useful in a moment. So now I want to describe isofibrations. So we know, for example, that we can describe, well, other fibrations that we're interested in, like left fibrations, right fibrations, inner fibrations, as the right complements. So, and the isofibrations has a different definition. So I want to show that actually it is possible to write isofibrations as a right complement. Okay, so to do this, I need to recall that before I introduced I, that was a groupoid with two objects, and the only non-trivial maps are two isomorphisms. Now I want to fix notation J. This is the nerve of this groupoid. Some Simplicial set. Well, of course, this is an infinity category. And I also want to fix notation for the canonical map U. This is a map from the delta 1 to the J. Right? So we can immediately, well, delta 1 is the nerve of the category with two objects and one map. Obviously, there is a functor from such category to this groupoid, and then we apply nerve to this and get this map of Simplicial sets. Maybe let me write this. So this is the same as this is the nerve of the one under, well, we have one underlined, this is mapped to the I, and this is the canonical inclusion, and this is the nerve that you apply to this thing. So this is very easy definition. Then there is a combinatorial lemma, that is one of the problems in the last assignment, is to show that U, so the map U is anodyne. And I want to use this combinatorial lemma to prove next proposition. This is a way to characterize isomorphisms in an infinity category. So let C be an infinity category. Let's assume that we given an edge or a map, so F is a map from delta 1 to the C. So the map F is an isomorphism if and only if, well, there is another map F prime from the J to the C, well, such that F prime composition with U is F. So you can kind of factor this through the, so we have delta 1, it is embedded, mapped to the J, so this is map F, right? So this is U, and this is F prime. So a map is an isomorphism if and only if you can factor this through this Simplicial set J. So of course, if you do this for the categories, not for this infinity categories, this is more or less obvious. Well, you have this just another arrow, and this will, if you apply the, if you just look at this arrow in the category, right? This is lives here. You apply a map to the category. This will be the inverse arrow to this arrow. So this is easy for the categories, and also not that hard for the infinity categories. So for this reason, sometimes this J in the infinity category theory is called something like freestanding isomorphism. And in the usual categories theory, this I also sometimes called freestanding isomorphism. Okay, so the proof, of course, in one direction, this is easy, right? So if I assume that I have such factorization, well, then clearly this is an isomorphism. Again, by the same reason. Now I just want to use some, again, lifting problems to go in the other direction. So I want to construct the this f prime that I promised in the statement as a solution of some lifting problem. Okay, first of all, since now I know that f is an isomorphism, I can also write it as follows. So I can take given map f and then kind of decompose this into the f, say, tilde to the maximal subgroupoid, and then there is an inclusion of the maximal subgroupoid into the C. So this is still the same f, right? Using that f is an isomorphism, I can always present it like this. So there is a map to the maximal subgroupoid and then inclusion of the maximal subgroupoid to the C. Okay, so then for this f tilde, I want to look at the lifting problem. So let me take delta 1. With the map f tilde, I can map this to the C with tilde. So C with tilde is mapped to the star. And then there is J mapped to the star. And this is map U. Okay. So now I want to understand that I have a solution of this lifting problem, which will be by definition, you can see that the solution of this lifting problem is exactly this f prime that we need to find, right? And why this f prime exists? So maybe I can ask you this question: why we have f prime? Well, we know that the map U that we have on this diagram is anodyne, right? So we have a solution. Well, the anodyne means that this is in the weak saturation of the inclusions of all the horns. And to have a solution, this has to be a fibration. But this is a fibration if and only if this is a Kahn complex. But now we know this infinity groupoid, and this is the Kahn complex. So this is the Kahn complex, and we have then we have the solution of the lifting problem. So I need to write this. So since U is anodyne and C is a Kahn complex, there is a solution or lift. There is a lift, and we call this f prime. And this lift f prime is exactly what we need. Okay. So finally is the statement that I promised. I still have enough time. So the statement that I promised is the following. So proposition so let, as before, P be an inner fibration from C to D. Inner fibration of infinity categories. So then the following are equivalent. Well, really, just two conditions. So first is that the P is an isofibration. And condition 2 is that I have a solution of the lifting problem. So here I have an inclusion of the 0 into the J. And I need to have a solution of the lifting problem with P on the right. So these two conditions are equivalent. So we can see that actually we can formulate that the class of inner fibration is something like a right complement to some other class. So in particular, we immediately get all the nice properties that this class is, for example, co-saturated, in particular closed under pullbacks. That's kind of nice to have for any fibrations. So proof. Okay. So let's start with 2 implies 1. So in condition 2, I'm given that I have a solution of some lifting problem. So maybe just let me write this lifting problem. So this is the lifting problem for which I know I have a solution. Right? So for such lifting problem, there is a solution. So I'm claiming that this implies the existence of a solution for a lifting problem that I used to define isofibrations. And that was the following. I took 0, included this into the delta 1, and that was solution of the lifting problem where instead of C, I used the maximal subgroupoids for C and for D. Right, so. Right, so is it clear that if I have a solution of the lifting problem like this, I'm also have a solution of a lifting problem like this, right? Because if I have this solution, right, this is a map from the J to the C, so it represents some edge or arrow in the C, but this is an isomorphism since this is not from delta 1 but from the J. So that's exactly what I need, right? If I need to have a solution like this, I need to know that this map is an isomorphism in the C, right? Given that this is an isomorphism in the D. But this is indeed the case since I know that this is an isomorphism in C. So if I have a solution of this, I immediately have a solution of this. Okay, so this was in the one direction, and in the other direction is a little bit more interesting. So 2 implies. Sorry, 1 implies 2. Yeah, so I want to solve some particular lifting problem. Right, so let me maybe formulate this problem. So let me take again 0. Let's call this map first map A. This will be mapped to the C. There is an inner fibration P to the D, and then there is J. And the inclusion of 0 into the J. I want to call this inclusion from 0 to the J by a little j. So I hope this is not confusing. So I want to solve this lifting problem. Well, this little j, I can write this as a composition. So I can write that the little j is the composition of the U, so the same U as before, the canonical map from delta 1 to the j, and the little I, where this little I is just the inclusion of the 0 into the delta 1, right? Clearly this is a composition of this kind. And I will solve this lifting problem by solving 2 other lifting problems. So maybe let me call this lifting problem star. So, and say that we solve lifting problem star by solving 2 lifting problems below. So the first one is the following. So I take, I can take 0, the map A prime to the maximal subgroupoid of C, and then inner fibration which induces an inner fibration of the maximal subgroupoids, and then delta 1. So this map will be the composition of the B prime and U, and this is I. So here I'm using the following notation. Maybe I need to write it somewhere. So the, for example, for B, so the B, where it was, so the B is my notation for this arrow. I didn't even introduce this. So B is from the J to the D, and then I can kind of decompose this and consider this as a map from the J to the maximal subgroupoid of D, and then the inclusion of this maximal subgroupoid into the D. So this first map is, I'm going to call B prime, right? Since this is from the J, right? So the so this is a map from the some concomplex or infinity category to the D. It's always length in the maximal subgroupoid, and the same is true for the A. So A as a map from the 0. Well, I can I'll take this map from the 0 to the maximal subgroupoid of C, and then the inclusion into the C, and this is called A prime. So this is how I introduce maps A prime and B prime. Okay. And you can verify when I'm erasing the blackboard that actually given the commutativity of that square, this square is also commutative. Right, and this square has a solution. Well, because this is kind of the setup for the isofibration, right? I start with an isofibration P, then the restriction to the maximal subgroupoids. This is another isofibration, by what we proved before using Giles lifting theorem. Well, actually, this doesn't use anything. This is simple. So this is isofibration, and there is a solution. So the fact that the inner fibration induces on the maximal subgroupoids in isofibration give us the solution. So this solution I'm going to call T. So there is T. There is T. So now I'm using this T for the second lifting problem. So take delta 1, use T as a map to the maximal subgroupoid of C, then this is mapped to the maximal subgroupoid of D, this is J, this is the canonical map U, this is still B prime, and again this is commutative, right, because for example in this lifting problem this triangle is commutative, so that's a commutative square. And again I'm claiming that there is a solution C prime of this lifting problem. Well, this is because the map U is anodyne and P is a fibration. So here for this claim I'm using Giles lifting theorem, so P core of P is an isofibration, hence a fibration. So these two conditions together give me that there is a solution of the lifting problem, which I'm going to call S prime. Okay, so I solve these two new lifting problems, and then, well, I claim, well, there will be some, I need to know that, so this S prime, this is, so let's define S. So the S prime is a map from the J to the maximal subgroupoid, and then there is inclusion of the maximal subgroupoid into the C. So the primes is for the maximal subgroupoids, and without primes is just for the C. So I constructed the map from the J to the C. That's the definition of the map S. That's a composition of the S prime that I constructed before with the inclusion of maximal subgroupoid into the C. Okay. So now I just need to verify that this is indeed the solution of this lifting problem, that these two triangles are commutative. But this follows from the commutativity of some triangles that I have. For example, if I look at the, say, S prime composition of the U and I, which I called little j here, right? So then the way it was constructed, this is the same as the composition of the T and I, and if you go back at the definition of the T, this will be precisely the same as the A prime. So it means that kind of before I include this into the maximal subgroupoid, I get the one of the identities. So the S. So this is this is the problem. So this is S here, right? So and I need to verify, for example, that the composition of the S and J, which is that composition, is A. But I have this with the primes, and if I have this with the primes, I have this without primes, since the primes are just inclusions of maximal subgroupoids. And the same is true for the second identity. So the composition of the PS will be equal to the B. So kind of just by hand construction of the given lifting problem, by reducing this, since this is a composition, I can reduce this to the solution of the other two problems. Maybe this is not the optimal solution, but it's kind of very simple. Okay. Okay. So let me just, to finish the lecture, formulate several corollaries. So the first one, I want to write isofibrations. So I want to write this as a right complement to something. What is something in the parentheses? What I need to put as an argument of this right complement? No, we proved this theorem, right? So, and also, I also in the proof I call this map, this inclusion map J. Right? So if you look at the statement, what's the argument of that right complement? Well, if you simply say that this is J, it's not correct, right? Because we're given that this is an inner fibration. So the right class to which we need to apply the right complement is the inner horns union with this map J. So from this, we immediately see that isofibrations is a co-saturated class. In particular, what's usually used in the application, that this is closed under pullbacks. And last, very simple corollary is that, for example, any trivial fibration is contained, or trivial fibrations, any trivial fibration is isofibration. So the class of trivial fibrations is contained in the class of isofibrations. The proof is really just one formula. The definition, the definition of a trivial fibration was that this is, the definition was that this is right complement to the inclusions of the boundaries, right? But this is the same thing as the right complement to the inclusion to the class of monas. So since inner horns and also map J, these are all monomorphisms. If you take the right complement, we will exactly get this inclusion. Okay, I think I'm out of time. Yeah, I'm almost out of time, but I don't want to go to the next statement because it's long and technical. It doesn't make sense to just formulate it and do the proof next time. So I stop here.